record button. We left off obviously talking about the different levels, so to speak, of how the base of your energy systems is going to be fat metabolism aerobically, followed by carbohydrate metabolism aerobically, and then we work our way up. Now, keep in mind, obviously, the speed of which we can get energy produced from an energy system is inverse related to how long that energy system can last for. And so now, the ATP PCR, we're just out of phosphocreatine. We're low enough on ATP that we can't keep up that power output. Now, anaerobic glycolysis, the reason that shuts down is because the pH drops so low that literally enzymes don't function like they're supposed to. Aerobic glycolysis is going to stop helping us because effectively we are doing enough work that we've pretty much emptied that gas tank. And glycogen is a fascinating molecule in that it's not one long strand, it has multiple branches of carbohydrate. So as you actually deplete your glycogen more and more, it's not a linear relationship between your glycogen's down and your performance is down. It's actually as your glycogen drops, your performance drops faster. So outside of that, we then have the beta oxidation, and that pretty much never runs out. It just turns out it's not that fast. Yes, you could run out of fat, but it's probably not going to happen to any of us. So what questions you guys have about chapters 1 and 2, from how muscle contracts to muscle fiber types, how we've got those hybrid fibers, so on and so forth. Any questions there? Any questions about the energy systems inside of the cells and how they work?
Could you just go over like what each one would be used for again, like the ATP, PCR, like which?
Yeah.
And maybe an example of which exercise, I guess, or like the times.
Think of it as the time and the intensity.
Okay, yeah.
No, this is a custom slide that I made, Zaria. But you can go ahead and take a screenshot of it right now, and you just got to hit Control, print screen, and then you just got to paste that into a Word document and you'll have it. So to answer Colleen's, remember we're always using all the energy systems. The key is which we're emphasizing the most. So like a true maximal 10-yard sprint, 20-yard sprint, that's pretty much the lion's share of all of that energy is coming from that ATP PCR. Now, if we're going to say like a maximal 400-meter sprint, about 70 to 80% of the energy produced there is going to be from that anaerobic glycolysis. Now, it's fitting since you're a long distance athlete, your 5K time is pretty much you running on purely aerobic glycolysis with obviously a little bit of anaerobic glycolysis. And then your ultra marathon time is going to be a lot closer to your beta oxidation. When I say ultra marathon, guys, I'm referring to 100 miles. So it's just naturally going to be a rather low and slow speed. Now, remember, they're never in a bubble. So right now, most of us are running heavily on beta oxidation with probably a little bit of aerobic glycolysis. But let's say we're going to go for a run, or, we'll pick the ones of you guys that actually do run. So when you guys are going to be, going for a run, meaning you're going at a pretty decent clip, you're going to be having some muscle fibers inside of your muscle using anaerobic glycolysis. Some muscle fibers are going to be using aerobic glycolysis, and even some fibers are going to be using beta oxidation. Now, the key is your type 1 fibers are going to be the ones that are more likely to use beta oxidation and aerobic glycolysis. And then your type 2 are going to be the ones that are more likely to use anaerobic glycolysis. So remember, it's what fibers are we tapping into in that individual muscle itself. Now, remember, the energy systems that we train the most in is where we're going to see the adaptations specifically to those demands. And over a long enough period of time, we'll start to see transitioning also in your muscle fiber type to start to show more of effectively the interaction between your own genetics and then obviously the training intensities or training modalities that you're most likely to use. So does that answer your question, Colleen?
Yeah, so the ATP PCR and anaerobic glycolysis would be with type 1 fibers, and then the other two with type 2 fibers.
Remember, type 2 is your speed and your lack of endurance fibers. Your type 1 is your aerobic. And all fibers have the ability to do each of those. The key is which are they the best at? So your
Okay.
type 2 fibers are typically much better at the ATP PCR and anaerobic glycolysis. And then your type 1 are typically better at the aerobic glycolysis and beta oxidation.
Okay, thanks.
Anytime. Any other questions over anything we've covered so far, guys? So everybody's been getting perfect scores on the quizzes. They don't have anything they want to go through? Yes. A marathon is going to be aerobic glycolysis with a solid amount of a solid amount of beta oxidation. Sorry. Your marathon time is going to be something probably along the tune of 60 to 70% aerobic glycolysis, and then 30 to 40% beta oxidation overall. And obviously, guys, keep in mind, it's the muscles that you're using for what you're doing. That's okay, Courtney. If you remember it, just drop it into the, just drop it in here and we'll make it happen. All right, guys. So we feel good on our energy systems. Then we're going to move on along and get into our neurological system. Yes, Haley. Negative feedback is going to be, oh, sorry, that's when we're going further on. Let's go to where we need to think about it, right? I'm teaching, so please come back. It would help if I would keep, so negative feedback is where we're going to go ahead and have the products of another reaction are going to go and inhibit the first enzyme from functioning. So that way we never have more of anything than we ever need. So effectively your body's only trying to break down the minimum amounts of glucose, fatty acids to give you the energy you need to keep going. Because obviously you don't catch all of that energy from breaking down food. We're usually about 30 to 40% efficient. So the rest of the energy from breaking down food is released as heat. Hence why, when you burn calories, you warm up. And so you're going to find that if we happen to be breaking down more things we need to, we're wasting energy. And an animal that's really good at wasting energy is not an animal that tends to keep passing on its genetics. So negative feedback is effectively all about limiting. So you never go too overboard on anything. Okay. Yeah, no worries. So glycolysis itself has an activation energy cost of 1 or 2 ATP. 1 if we're coming from glycogen, 2 if we're coming from just a plain glucose. And we are going to generate 4 net gross ATP going through glycolysis, but we only net 2 of them. If the activation was 2, if the activation was 1, then we net 3. Now, when it comes to the citric acid cycle, we're actually only producing 1 ATP per pyruvate that gets fed in and goes into acetyl-CoA and all the other steps. It's actually GTP that converts into ATP. The key is we generate a lot of NADH and FADH too. So the generation of all of those components is what's going to lend itself of this NADH. And remember, we're going through this twice because we made 2 pyruvates out of 1 glucose. That in turn is going to give us that total yield where we've got the GTP and ATP from glycolysis in the Krebs cycle, but then we have all that NADH and FADH2, which in turn is going to be where we're really netting the major energy from the electron transport chain at the very end. Good questions, guys. Anything else you guys want to review?
Could you also go over a little bit more what's expected to like be included in the limits to muscle size assignment?
Okay, so this one it's meant to be a challenging take-home assignment. This isn't meant to be something you can just like Google, why do muscles not get any bigger? We've got a lot of different things going on. So we've got cellular signaling, so the actual signaling on the inside of the muscle to get bigger or to maintain that size. We've got myonuclear domain theory, which the basic idea is we've got, skeletal muscle is fascinating that we can have more than one nuclei inside of the muscle. And so it's equivalent to saying we can have more than one factory inside of the muscle, building more proteins that allow us to contract our muscles and so on. So if we can get more factories in there, in theory, we can go ahead and make that muscle bigger. So think of it this way. If we have one person who's doing all this farming by hand, that one person can only effectively farm so much land. Yes, they could probably farm by hand, meaning turning the soil by hand, everything else by hand. They can maybe take care of an acre or two. So the only way you could take care of more land in this example without the use of added technology is you need more farmers. And so if you have more farmers, now we can take care of more land, aka we can have a bigger muscle. And so if we can get more and more farmers, then we can have more and more muscle. Now, the other hypothesis, or one of the many, is that it comes down to capillary density. So literally getting enough blood flow and nutrient delivery and waste product removal to those individual fibers so that it can support a bigger size. So if it doesn't have enough around it, you're not necessarily going to be able to get much bigger. There's another theory that it actually is also related between the crosstalk between muscle and bone, in that you're not going to find individuals with really large muscle masses that also don't have really high bone mineral density. And the basic idea for that is your bones have to be big enough and strong enough to deal with all the forces that your muscles can produce. Because if they're not, you're going to have a bad time. So that's kind of a shorter list. And there's some other potential options out there as far as what limits the size of skeletal muscle. You can look into myostatin, myostatin, and how that can be influencing muscle mass. But that's a pretty good start for you guys. And I've given away way too much for that homework assignment. Haley, figure it's probably going to be at least probably like 2 pages. Like anything else, I can definitely tell you that the ones that tend to write more, and it's not fluff, it's actual like content and information. And remember, I want you guys to try to reference where you're getting this information for. They tend to get the better grades on the assignments. So it took me, a couple minutes to talk through the basics of everything that you have to cover with obviously not doing any referencing. So you're probably going to have to put in more content than that in order to make sure that you hit that out of the park. You're all good. The other little order of business while we're just kind of talking shop is for the lab. Obviously Friday, you're doing that reps to failure, looking relationship to muscle size. We're going to have girth measuring tools. Whenever you first walk into the exercise physiology lab, it's going to be sitting on the table, on the desk where the computer is. And then same thing with the skin fold caliper. So you can do those measurements on yourself or your partner. Make sure you wipe them down pre and post. And there should be some wipes also there that you can just make sure you wipe it down. Throw on the gloves. Boxes will also be sitting out there on the table. And that way we can go through the data and analyze it as a group on Friday and figure out what we came up with. Any other questions? Yes, Courtney. The idea is that the lab for Friday, you're going to do that and the measurements on your own time. You could wait to do it until class, and it's just, lab will take a little bit longer on Friday. That's more than fine. But if you have the time and flexibility in your schedule that you can do it ahead of time, that's going to make life a lot easier on all of us, because we can just obviously all meet, go through our data, talk through it, and ask any questions you guys want to while we're in person, and then head on our merry way. So okay, good question from Haley, which is, where is oxygen utilized in metabolism? So that's a question for all you guys. Where do we actually use oxygen in all of metabolism? From glycolysis to beta oxidation to the citric acid cycle to the electron transport chain. Where do we actually use oxygen? Think in the actual metabolic process. So Raylan, we do obviously take it in through gas exchange. It's going to, obviously for the most part be bound to hemoglobin, then unloaded at our muscle cells, be picked up by the myoglobin, and then brought into the mitochondria. But it's actually not used for energy. It's actually a effective electron acceptor. So literally on this picture right here, guys, right there, that is literally where oxygen is utilized in all of metabolism. So literally oxygen is an electron acceptor. So it's gonna be bound with some of the protons, hydrogen. And from there, it's now literally, we've turned that oxygen into water. So technically, when you go through metabolism, you break down food, you actually produce a small amount of water. Carbon dioxide is going to be what's generated as we're going through the citric acid cycle. In fact, if we go back one slide, you can see where we're generating carbon dioxide twice early on in the beginning, and then the third time a little bit later on. And then notice when we convert from pyruvate into acetyl-CoA. So those are the points at which we're actually going to be creating carbon dioxide. So oxygen is just an electron acceptor that's going to go ahead and bind out some hydrogen, and congratulations, it's now water. So it's a tricky question, but it requires you to really think through what's going on with our metabolic processes. The funny thing is, pre all of the understandings of metabolism, was that they thought that literally inside of your lungs, there was essentially a fire that was constantly burning. And that's how we were turning over oxygen and turning it into carbon dioxide. Yeah, breakdown of chemical energy is going to typically be kind of a catabolism part of it. And this is going to be, remember, metabolism is all of the breaking down and building up at the same time. Anabolism is going to be building up. Good. Any other questions you guys want to go ahead? Yeah, that's because it's going to be catabolism. Metabolism is the combination of anabolism and catabolism. Anytime, guys. All right. So let's go ahead. We're going to talk about the nervous system. Unless you guys have got any questions you want me to go ahead and field, just drop them in as we go. We can always stop and talk more about that. So we've got our central nervous system, which is our brain and our spinal cord, and then we have our peripheral nervous system, that's everything else. Our sensory afferent, AFF, is going to be all the incoming information from our vision to our hearing, sense of smell, our touch, and our taste. Efferent is going to be the motor. That's the actual getting us to move. Now that has two branches, has the somatic, and that's what we're in control of, and has the autonomic, which is going to be essentially our fight, flight, and freeze response of the sympathetic branch, and the opposite side, which is going to be our rest, digest, which is parasympathetic. And that is something that we don't have that great of active control of, but we can tap into it. And we're going to learn it's incredibly important. Now, in order for any signal to go through, well, first we're going to have what's known as graded potential. So this is giving us a little bit of information of like whether or not we actually want to have a full action potential. So this is going to be both, they can be excitatory or inhibitory. So for example, if I was to just go ahead and just tap on the back of my forearm with my pen, like it's, yeah, I've got the touch receptors, but the pain receptors aren't turned on because I'm not hitting myself hard enough. But then if I took the pen side down and just went wham hard into my arm, that would be enough that we would send a big enough potential that we generate that action potential. And that's where we're going to have that signal going through the rest of the body. And that is only excitatory because that's going to make sure the rest of that channel effectively fires. So each individual neuron is going to have a resting potential, okay? When we allow for more potassium to go in, out of the cell, in turn, we are going to become more hyperpolarized. Whenever we have sodium go into the cell, we are going to be more depolarized. And once we hit a certain threshold, okay, that's going to open what's known as a voltage gated channel. And that's where we're going to have that action potential. And boom, the action potential is going to travel down the cell and then release neurotransmitters. And that will most likely cause that action potential to be generated on the following cell. So if a graded potential reaches about negative 55 millivolts, that's where we're going to see a action potential be generated. And now that information is going on. This is the all or none principle. So we either hit that threshold and get a contraction, or we don't hit that threshold and we get no contraction. Now, we're going to find that resting threshold is going to be about negative 70. So if we get just enough graded potentials that we get that sodium influx to where at negative about 55, then boom, we're going to go all the way up to positive 30 millivolts and then back down again. Now, this is going to be because of sodium going into and much more rapidly going into the cell, and then potassium going out. And this is going to occur in just a matter of milliseconds. So understanding effectively how all of this flows together is an important key for understanding, once again, signals going through the nervous system. So you can see our resting potential, we get the graded potentials until we get to the threshold. When we hit the threshold, boom, we've got this massive influx of sodium till we hit our peak where the sodium channels are going to close and the potassium channels are going to open. And now we're going to have potassium leaking out of the cell until we're not just going to hit the threshold. We're going to go not just to our previous resting potential, but we're going to actually hyperpolarize for a few moments. So if we were to look at this baseline, we saw it go down, that would be an inhibitory, essentially graded potential. If we go up, then we see an excitatory graded potential. And then once again, we can get ourselves the depolarization. Now, once we've had this action potential, we're going to have two different types of refractory periods. So this is going to be the absolute, which is no matter how much more signal we sent, we're not going to be able to get another action potential. And then our relative action potential, which is where with enough signal being sent, we're going to be likely to be interested in doing something like that again. So, how many of you guys have ever, so a good example would be like of an absolute refractory period would be like, think of any time you've eaten way, way, way too much of any dessert, where it's like, nah, like you couldn't have another bite if you wanted to. You're like, I'm good, I'm done. Please God, let it stop. Whereas the relative refractory period is the point of which where it's like, yeah, I've had a lot of cake, but I could probably have some more. Okay, good for you, Courtney. You can also apply this to drinking if you guys do partake in that, and I'm not here to judge. Trying to think of anything else that'd be a good reference, but the basic idea again, absolute does not matter. You are not going to be able to get another action potential to occur. Relative is with enough cajoling, you can effectively make it happen. So these action potentials are going to propagate down the axon. And what's neat is thanks to myelination, which effectively is fat wrapped around those axons by what's known as Schwann cells, that we're going to get what's known as saltatory conduction, where it's going to literally be able to skip the fat wrapping it and go faster down the nervous system. In fact, this is a big part of motor learning, and hence why when we talk more in bioenergetics about nutrition, why things like appropriate fatty acid intake, specifically when we're looking at omega-3 fatty acids, to make sure that our nervous system is able to repair itself and also to allow us to learn appropriately. Now, aside from myelination to allow that signal to go faster, we can also increase that axon diameter, so that way the signal is going to be able to go even faster. Now, when we get to the end of one neuron and the start of the next, or this can, in this example, this is going to be between the end of the neuron and the muscle itself, we have literally the neuromuscular junction. It's very simple. Now, this is where our neuron, because of the action potential going down the end, it's going to signal the release of those vesicles, just little storage packets that have acetylcholine. That acetylcholine is then going to be released into that synaptic cleft. So it's going to go through essentially the neuromuscular junction to the other side, and it's going to bind to what is known as the acetylcholine receptors. And once it binds to those receptors, that's when you're going to start to have that depolarization. And if you have enough of that depolarization that we hit that threshold, boom, we have an action potential that's going to travel out of the neuromuscular junction, down the plasmalemma, so the cell membrane of the muscle fiber, and into the T-tubules, and then boom, you're going to start to get yourself a contraction. Now, this can be sent at a fast enough rate that the muscle cannot fully relax in between each of these signals. And that's a good thing, because that's where we're going to go from just going to twitch to a full fused tetanus, where we're going to have maximal force production. So there is a whole lot of different neurotransmitters that are going to have effects on anything from attention to learning to focus to, being happy. And we're going to find that we have effectively two major categories there. One is going to be the smaller rapid acting, and the other is going to be larger, more slow acting. So acetylcholine and norepinephrine are big components of exercise. Acetylcholine for our muscular contraction. It is also the neurotransmitter of our vagal nerve to our heart to get us to relax for the parasympathetic tone. And norepinephrine is going to be an important part for the sympathetic nervous system action, and epinephrine being the other hormone that's going to go through us. Now, norepinephrine also helps you learn and focus. And that's why I'm sure some of you guys, after a good workout, but not one that just brutalized you, you're going to find that it makes it a little bit easier to kind of study and focus up for about an hour or two after you get done working out. Now, once we go ahead and have these effects on the cells, we're going to then in turn have effectively these postsynaptic responses. So these are neurotransmitters which are going to give us greater potentials in the cell. Excitatory, remember, we're getting ourselves close to that threshold. Inhibitory, we're going to be hyperpolarizing. So, for example, drinking a lot of coffee, doing a lot of, caffeine or other types of stimulants, that naturally works as kind of excitatory effects on our skeletal muscle system. So you're going to find yourself, you're a bit jumpier. It's easier to get muscles contract without trying to. Whereas, obviously, being tired is one of them. Inebriated otherwise are going to be ones that are going to cause an inhibitory postsynaptic potential, or just fatigue from training, where it's going to be harder and harder to go ahead and get those muscles to contract. So, any questions about the basics of just getting our neurological tissues to fire to do what we're looking for them to do?
Okay, so you're talking about this whole like action potential thing. Does that happen anytime you like move a muscle, or is that like
Yes.
so it just happens like all the time, anytime you move or anything?
This is literally how you get the body move. That's why, unfortunately, people that have had their spinal cord severed, they're paralyzed. They don't move. They do twitch on occasion, just because you can have some, localized changes in your gradients that can sometimes cause an accidental muscular contraction, cramping that we talked about beforehand. But as far as like a full blown, you choose for volitional movement, and you do have some reflexes that are going to go through the spinal column. So don't forget about that. But as far as like you want to pick up the pen and write something, that's all coming from your nervous system. I'll take it as that was at least a slightly adequate answer to it. So now we're going to talk about, obviously, the brain itself. So the first thing we have is the cerebrum. That's going to be our higher part. Now, in the frontal lobe, that's where we're going to have our motor cortex. And this is going to be, where we're making conscious decisions. We're going to go from the pyramidal cells to the corticospinal tract to the spinal cord, and then going obviously out into the body. Our basal ganglia is going to be essentially the white matter in there, and this is going to effectively give us the organization for repetitive movements and allowing us to do it without thinking. So think about how easy it is to walk, to run, without having to really focus on it anymore. You can hold a conversation, you can chew gum, etc. But if I was to have any of you guys try to ride a unicycle and try to even ask you a simple question, well, you're going to be falling all over the place because you're still working on developing that skill. And the basal ganglia is one of the parts that effectively allows you to come to the solutions. All movements are literally just problems that your nervous system has to solve. And obviously some people's brains are better at solving movement problems than others. But we're still looking, when we're working with athletes, it's literally a brain that's learning, and it has to learn that skill. It has to refine that skill. And you're literally talking about tissues that have to effectively adapt and update themselves to whatever stressor you're applying to them. Now, our sensory cortex and our parietal lobe, that's going to be giving us information as to what's going on. What are we feeling? Where is our body at in space? Temporal lobe, now we're talking about our hearing. Occipital lobe, we're talking about vision. Our diencephalon, we're talking about our thalamus and our hypothalamus, thalamus being the major processing component of the brain, hypothalamus being the major control of, essentially, the major thermostat of the body. Controls the pituitary gland. Pituitary gland, as we'll learn with the next chapter, is the master gland for the body. We then have our brain, which is going to be important for a number of components. Our pons and medulla oblongata, which is just regulating things like breathing and effectively heart rate to keep us alive. Our cerebellum, which is going to not be part of the cerebrum anymore, but that's going to be what's helping us refine our movements, so they're going to be effectively as simple as they can. And we're also going to talk about the hippocampus and the amygdalas and their importance for just overall performance or health as well. So we have the wonders of the thalamus. Now, right now, guys, you are getting sensory information from your eyes, from your ears, from your olfactory sense, from your taste receptors, from all of the different touch receptors. How do your toes feel inside of your socks, your shoes right now? Now, before I said that, how many of you guys were even thinking about that? Good, Courtney. How many of you guys are thinking about the waistband of your, shorts, pants, whatever you're wearing? Like how many of you guys are aware of how the collar of your shirt sits on your body, etc., how your jewelry feels? How many of you guys who have ears pierced even think about the fact that you have a piece of metal shoved through your skin right now? It's not so much that it isn't painful, but we're also not trying to put any attention there. And the thalamus is where we're going to be doing a lot of that attentional gradient. So we can only actively perceive about 1/10 of the total information that we can take in each second. And the thalamus is how we're able to go ahead and pay attention to one thing or another. You know, that's why if you're trying to listen closely, sometimes you'll see people shut their eyes. So that way they don't have to worry about any other information coming from that area. And the same thing, if you're really trying to focus on, you know, seeing something, you're probably not going to be listening as well. We have a finite amount of bandwidth for what we can actually pay attention to. And the thalamus is going to be the major part of kind of, okay, let's focus on what we need to focus on. Hypothalamus, like I said, regulating homeostasis. And that's just trying to effectively keep the body in balance, that all of our tissues have enough oxygen, that we have a pH in the level that it needs to be. We've got fluid levels and electrolyte gradients where they need to be. Quite possibly, and that's also why you'll see people turn off the radio when they want to check the map or something else along those lines. Just remember, guys, the key to multitasking is doing 2 jobs poorly at the same time. Because we really suck at multitasking. Humans aren't good at it. We're really good at doing one task at a time, even though it's boring. Evan, it's probably not really going to be something where you can really increase the amount of info you can perceive at a given time, but think about your ability to pay attention to the things that matter at a given time. So, you know, we can all experience the same event, but if everyone's looking in a different direction, then we're not all going to see the same thing, and we're not all going to perceive the same thing, because it turns out it's the joys of being human and having differences in how we, not just what we're taking in, but the other thing that blows my mind is then also how we have differences in perceptions of the same information. You know what? We're working ahead, so I'm bringing up something wild. Okay. So now we're going to do something definitely a little funky, okay? I want you guys, I'm going to play a little clip. First and foremost, let me know if you guys can hear what I'm trying to play, okay? Hopefully I can get this to work pretty quickly. First, I need a stupid ad. Not about it. All right. Can you guys hear that? Okay. Type out what you guys think that is saying, but don't hit return yet. Don't put it in the chat. Just type out what you think this is saying. Okay. Now, when you're ready, go ahead and hit enter and put it in the chat. Yeah, what do you think it's saying? That is literally a recording of the word laurel, L-A-U-R-E-L. Now, part of it is probably the fact that my wonderful computer is not that great. But the other part is literally how our brains interpret information. There is a solid amount of people that will listen to that and they hear the term Yanni over and over again, which is, yeah. I have never once heard Yanni any single time that I've listened to that. And that's not one of us is right, one of us is wrong. Exactly, Courtney. It's like the blue and gold dress. That's literally showing us the difference between how our own nervous systems will effectively interpret information. And that's how literally two humans can see the exact same thing, but get differing reactions because of literally little subtle differences in how we are wired. It's not you're right or you're wrong. Yeah. Yeah, it's also, let's face it, it's the computer picking up the sound from the speakers playing to you guys. So there's definitely something lost a little in that transition. But you can go ahead, that's why I threw the link up in the chat that you can listen to it on your own. Well, actually, I should probably just put it also here for anybody that wants to see what they, or wants to go ahead and give that a go or impress your friends. Now, the brainstem itself, this is going to be the relay of information between the brain and the spinal cord, where we have the midbrain, the pons, and the medulla oblongata. We also have the reticular formation, which is going to give us the basic muscle function and tone, along with our cardiorespiratory function. So part of the muscle tonus you walk around with is thanks to effectively how well charged up your nervous system is for activating different musculature. And then we have our analgesic system, which is going to be where we have our natural endorphins produced that help modulate pain, which are not all of it. Obviously, cannabinoids are another part of it. But what's fascinating is if you run about, I think it's like if you run a 10K every single day, it's about the equivalent of doing like 5 milligrams of morphine, or there's some type of conversion like that. So I'm not calling our long distance athletes here drug addicts, but I am, no, I'm kidding. But what they're doing is they're naturally producing those opiates from their own exercise. They're not having to use it from, unfortunately, a number of endogenous choices that a lot of people fall prey to. And let's be honest, it takes a lot more effort to produce that natural endogenous opioids from long distance running or from cardio in general than it does from, drug abuse. For my cross country athletes in here, when do you guys typically hit your runner's high?
For me, it's like not that long after, maybe like 5 or 10 minutes.
Yeah, same for me.
Yeah, so what you guys are saying is you're just trying to chase that dragon every single day. You need to get your hit.
Yep, that's why I keep running.
No, but I mean, it's fascinating. And there's nothing wrong with, like anything else, having a good physical practice. So now let's talk about some sensors. We have what's known as our joint kinesthetic receptors. These are literally telling us where our joints are at in space. That's why you can wake up and know in what position your body is in. Meaning, like you guys maybe fall asleep and you roll around in your sleep and you wake up like, I'm in this position. Now, if you sleep funky on like one of your arms and you wake up with a numb hand, you're like, where is this thing at? Like it's flopping around and it's not fully making sense yet. And that's because we're not getting that information. We then have what's known as our muscle spindle. This detects stretch on our muscles. So as our muscle stretches, it's going to cause the muscle to contract so we don't accidentally overstretch the muscle and cause it to tear, because it turns out a torn muscle is a bad thing. So you can just bend forward and try to touch your toes or pull yourself further, and if you feel in the back of your thighs, you feel on your hamstrings, you'll feel that tension naturally in them, because obviously they don't want to accidentally tear themselves. Then you have your Golgi tendon organs. Now these are stretch receptors that are literally inside of the tendon themselves. And so these are going to detect stretch on the tendon. When the tendon stretches, it tells actually the muscle to relax so you don't accidentally tear the tendon. And you're going to find that the muscle spindles, there is some difference between the muscle spindles that are wrapped around your slow twitch fibers and your fast twitch. And one's going to be a little more tonic, meaning firing effectively relatively quickly. One's more phasic, So there is a little bit of factors of effectively trainability here, in that what we're going to do when we train, our muscle spindles are going to become actually more sensitive. So we're going to do a better job of effectively putting a stretch on the muscle, getting the muscle to contract, and our Golgi tendon organs are going to actually be inhibited. So it's not going to tell the muscle to relax as early. Now, of course, this can be at the detriment of our own health if we take things too far. So we then have our happy, wonderful sympathetic and parasympathetic nervous system. And so this is going to be the sympathetic side, which is going to be the fight, flight, or freeze. And then our parasympathetic, which is going to be our rest and digest. And so you're going to find, obviously, if you guys can hopefully read this well enough and see what's going on, I want you guys to kind of think through like, oh, okay, you can feel how this is going to get you ready to go ahead and effectively fight, so to speak, or get ready to do something when it comes to sympathetic nervous system. You know, our heart's beating faster. We're going to have some vasodilation to the heart itself, but then we're going to go ahead and have effectively some bronchodilation. We're breathing more, along with slight constriction of blood vessels. That's the epinephrine. Epinephrine is a global vasoconstrictor, which is really cool. And that's where people, you might say that they got, someone was so scared they turned pale. And that's literally because now they don't even have, they've got so much vasoconstriction globally, they don't even have that good of blood flow to their skin. Now, it's a great thing because if you're working out, all that blood flow only goes to your exercising muscles, which is going to in turn enhance your performance. But if you're just scared because you're about to give a presentation, otherwise, it doesn't actually do you a lot of good. In fact, it actually makes it harder to think good. And then the opposite is going to be for the parasympathetic. It's about resting and digesting. So you're relaxing, you're getting better overall blood flow. You're going to go ahead and be able to effectively do a better job of recovering. So we want to be in good sympathetic tone, or at least enough of it when we're training, when we're playing our sport, but we want to effectively spend the rest of our day in parasympathetic, mostly relaxation states, because that in turn is going to allow our body to recover at a much faster rate. What questions do you guys have for me? We got about a minute left, and I wasn't sure if there's anything else you guys would like to ask questions on or cover.
Is this PowerPoint on Blackboard?
Yep, like all. So